Hello everyone, today we are going to answer some important questions. The first one, how do the calculated energy levels change with the number of discretization points? Well, the first thing we need to understand is how the number of discretization points affect the accuracy of our energy levels. Basically, the more points we use, the more precise our results will be. As n gets bigger, the energy levels we calculate became closer to the actual value of the system. But increasing n also takes more time and more computer power, so we need to find the right balance between accuracy and efficiency. Okay, so now the next question. Are the computed wave functions orthogonal to each other? Let's talk about whether wave functions or eigenvectors are orthogonal. This means they should be perpendicular to each other. In quantum mechanics, wave functions form different energy levels that should be orthogonal. To check this, we can calculate the dot product of two wave functions. If the result is zero or really close to zero, it means that they are perpendicular, which is exactly what we want. The next question is, how do the energy levels change if the effective mass of the particle varies? What happens if the effective mass of the particle change? This can happen in materials like semiconductors, where different particles have different masses. A smaller effective mass leads to a higher energy level, while a larger mass lowers them. This is important when working with different materials because it affects how energy works inside of them. Perfect, so now we are going to answer question 4 and 5. Question 4. How close are the computed energy levels to the theoretical values for an infinite square well? We compare the energy levels we calculate with the theoretical values of an infinite square well. The formula for an infinite square well is very precise, and as we increase the width of the well, our computed values should get closer to this theory. But if the well is too small, we might see some differences because the system isn't behaving exactly like an infinite square well. And the next question, how do the energy levels change as the width of the infinite square well is varied? Now, let's see what happens when they change the width of the square well. When the well is narrower, the energy levels go up, and when the well is wider, the energy levels go down. This because in quantum mechanics, the more confined the particle, the higher its energy. Okay, now so our last question, question 6. How can the discretized Schrödinger equation be transformed into a matrix form? We can transform the Schrödinger equation into a matrix by dividing the space into a grid of points. This grid helps us build a tridiagonal matrix. Solving this matrix gives us the energy levels, which are the eigenvalues of the matrix. And this process allows us to find energy levels numerically. Okay, so in conclusion, we've looked at how the number of discretization points, wave functions, orthogonality, effective mass, well width, and matrix calculations all influence energy levels in quantum systems. And by understanding these factors, we can make sure our results are both accurate and efficient. Thank you.